This is the final lecture in terms of learning one-dimensional finite difference time domain. We have a lecture or two after this, stepping you through examples and stuff like that. But so this will be the last learning one. We will start off by reviewing lecture 6. And in this lecture, we're going to add two more things. We want to talk about this more sophisticated source, the total field scatter field source, which we can also think of as just a one-way source where we launch a pulse from left to right and nothing propagates backwards. Then the last thing we want to do is figure out how to calculate reflectance and transmittance. And usually that's in terms of frequency, so we also need to learn about Fourier transforms in the context of finite difference time domain, and also a little bit about displaying the results. We talked about Dirichlet boundary conditions, and to back up one small topic, the boundary condition. We are essentially writing a finite difference equation at every point in our grid. In fact, two, one for E and one for H. And at the very edge of the grid, one of our finite difference equations requires a field value from outside the grid that we are not storing. So the manner in which we handle that is called our numerical boundary condition. This Dirichlet boundary condition is the easiest one. We just assume anything outside of the grid is zero. Well, if we're assuming that an electric field is zero, we have essentially placed a perfect electric conductor outside of the grid, and anything will reflect off of that. Likewise, if we assume a magnetic field is zero, we've essentially placed a perfect magnetic conductor at the edge, and everything will also reflect off of that. We talked a lot about calculating grid resolution, and one thing we needed to consider was resolving our wavelength. We needed to figure out what is the absolute shortest wavelength anywhere in the grid. So that comes from the maximum frequency inside the material with the highest refractive index. So we take that minimum wavelength and we want to resolve that with probably at least 10 cells. The other thing we want to consider is resolving features. And we probably have some minimum feature size in our grid somewhere. And we want to resolve that with probably at least one cell, maybe as many as 3 or 4. And so we have that consideration. So what we do is we take these two considerations, calculate a grid resolution, and then go with the smallest one, the one that leads to the smallest cell. Then another thing we may want to do is realize that we have a dimension that is really important to the operation of our device, and we want to get that right. And the grid resolution we just calculated may not lead to representing that exactly. So what we can do is then make that just a little bit smaller so we can resolve that exact critical dimension with a perfect integer number of grid cells. And now we have our grid resolution and we can go on with our algorithm. We also discussed this Courant stability condition. Numerically, a wave can only propagate one cell in 2 time steps. So if our physical wave would actually need to go faster than that, numerically our program could not do that. So we need to decrease that time step so that the physical wave won't outpace what our numerical wave can do. And that is called the Courant stability condition. I also mentioned in some crazy circumstances the refractive index can be less than 1, so we generalize this Courant stability condition to include that minimum refractive index. But in our codes, we're using this perfectly absorbing boundary condition, and in fact, we need a very specific time step that ensures the wave travels one cell in exactly 2 time steps. So we have an exact calculation for our time step. The Courant stability condition was considered in that for sure, but we don't need to consider outside of that. For our one dimension, we have that one exact equation, and I'll highlight it down here in the lower left. So we just calculate our time step this way, and everything else is satisfied. Then we talked about this perfect boundary condition or perfect absorbing boundary condition. And the conditions that allow us to do this is that, one, the waves at our boundary are traveling only outward. We don't have to account for waves traveling in 2 directions or bidirectional propagation. Also, the materials at the boundaries have to be linear, homogeneous, isotropic, and non-dispersive. And it has to be the same at either side. Given all that, we choose our time step so that the wave travels one cell in 2 time steps. We have an exact calculation. Now, since the wave is traveling exactly 1 cell in 2 time steps, we will know the field value immediately outside of our grid because it will be the same as the field value immediately inside the grid 2 time steps ago. And so that's exactly how we implement it, and we discussed that. Then we discussed a Gaussian source. What's great about finite difference time domain is that in one simulation we can excite it with an impulse which contains a huge range of frequencies. We simulate our device, and then everywhere we're interested in, we record those values as a function of time. That is the impulse response, if you will. And then at the end of the simulation, we can Fourier transform those, and then we know the impulse response over a broad range of frequencies, which I guess we wouldn't call the impulse response anymore. That would be the spectral response of the device. In this lecture, we'll be calculating transmission and reflection over a broad range of frequencies, but it's one simulation because we excite it with a very short pulse. And we choose some upper frequency limit that our pulse should include, and based on that we can calculate the duration of the pulse. And we came up with an equation. It's about 0.5 divided by that upper sort of cutoff frequency. We also said that if we look at our source as a function of time during the simulation, we don't want to start in the middle of this source. We want to sort of ease into it and ease out of it. So we have to delay the source a little bit, and we said we would delay it about 5 or 6 tau's, where tau is the width of the source, if you will. We also talked a little bit about how to estimate the number of time steps that your simulation will need, and we said at least 12 tau's. That ensures that we ease into the source and ease out of it. We also can calculate how long it would take a wave to propagate across the grid one time, and we add about 5 of that. And that's good for scattering devices or moderately resonant devices where the wave bounces around a few times. If you have something that's highly resonant, that's really not enough time, and in fact this isn't a good way even to do it. Instead, you'll track how much power is stuck in your model, and you just let your model keep going and going and going until finally that energy leaves your grid as either transmission or reflection, and essentially then when you're iterating all zeros or sufficiently small numbers within your grid, you can end. The last thing we did is tie it all together into one block diagram. And it went something like this. The first thing is calculating the grid resolution. And remember, there's the 2 considerations, the minimum wavelength, minimum feature size. But we come away with our grid resolution. Then we calculate our time step. We have a nice exact equation because of our boundary conditions here. Then we went on, we calculated the source, and we had a certain pulse duration based on the frequency content we want our source to contain. Then we calculate the update coefficients. There's 1 or 2 update coefficients really for every point in the grid, one for the E update and one for the H update. Then we set all the fields to 0. At this point we enter the main loop which loops over time. And first step is update H from E. Then we record the H fields at the boundary for our perfect boundary condition. Then we update E from H, record the E fields at the boundary. We eject a simple soft source at the middle for right now, and during this lecture we'll talk about the total field scatter field. We visualize the fields, and we loop over some number of steps, and then we're done. So that's where we are. Now we're going to add to it in this lecture. And the first topic is this total field scattered field source. This is a one-way source. So what we do is we divide our total grid. I'm showing a 2-dimensional grid here. We divide it into 2 regions. We have in the lower portion the total field region, which contains the source, and then the source bounces off our object and it scatters, and it also contains this scattered field. But this scattered field can pass through this region where we're injecting this one-way source, but it can pass through it and be transparent. And when we do that, any fields we have up here, we're guaranteed are traveling outward. And then on the bottom, we're also guaranteed they're traveling outward. We don't have another source down here that's injecting energy going up. So we just declare these 2 regions. The total field region containing the source and scattered waves, and then the scattered field region, which does not contain the source. Here we're sitting behind this region of the one-way source, so we're not seeing any bit of the source. We're only seeing fields that get reflected off of the object. So that's total field scatter field. And surprisingly, what we're going to do here is just declare this, write our update equations consistent with this, and our one-way source just appears. So let's say we did our simulations and we visualized the fields at a single frequency, just to give you an idea what all this looks like. So let's say we define our scattered field to look something like this, and total field, so the last 75% of the grid's the total field, and the first part's the scatter field. So if we launch a wave at some strange angle, we'd see something like this. There's no devices here, there's nothing to reflect, so all we see is that source wave. And then later on, when we learn this perfectly matched layer, we're watching it get absorbed. And so here's the materials. There's absolutely nothing interesting happening here. But then if we put some materials at the edge of the grid, now when this wave hits that, it will bounce off. And so what we're seeing here, the reason we see all these bright spots, dark spots, and this weird pattern here, we're looking at interference. We have an applied wave kind of traveling from the upper left to the lower right. It bounces off this interface, and then the reflected wave travels off in this direction. And we're looking at the interference between the applied wave and the reflected wave. Well, up here in the scattered field region, we don't see the source anymore. We're only seeing that reflected wave. So we see a pure plane wave, and then it's also getting absorbed in the boundary condition. This is not a boundary we've discussed yet. We're using a different one for this one-dimensional simulation, but this is coming when we get to two-dimensional simulations. You'll also notice on the other side of this interface, we see refraction. Our wave was originally coming in at this same angle. We used the same source, so it's this angle, and once it hits the material, it refracts, and the direction changes a little bit. Also, notice the wave fronts are much more compressed than they are up here. That's because we have a higher refractive index. No interference because we don't have any other sources down at the bottom traveling backwards. So we just see a pure plane wave in this material, and we also see it getting absorbed. So that'll give you an example of the types of things that you'll see in your model. Here's another one I did, I guess, just to show off, but it also illustrates this total field, scatter field sort of concept. We could, in principle, have a very complicated looking scattered field region. Of course, we'll have this one back here, we'll have our total field region, but we could put a bunch of points in the middle in the shape of a smiley face here for scattered field regions. If we run our simulation, remember, there's no devices. There's nothing for the waves to reflect off of, so there is nothing scattered. So what do we see inside these scattered field regions is absolutely nothing. They're completely green. But in the white areas, which is total field, we definitely see our source wave. Well, let's say we do the same thing again, but now we put this material down the bottom. Our applied wave hits that and reflects. So we see this interference pattern between the applied wave and reflected wave out in the total field region. However, let's look in the scattered field. Remember, the scattered field is just the wave reflected from that surface, which is exactly what we see in the scattered field, not only within the smiley face, but up top here. So scattered field regions, we're only seeing the thing that gets reflected from our device. In this case, it's a simple plane wave. Total field, we're seeing the source and the scattered fields. So hopefully these give you an idea of what you should be seeing in your model. Clearly with our one-dimensional models that we're doing now, things are much simpler. So here's a movie of a simple total field scattered field. And so what we see, we're launching a one-wave source. This is a rather slow simulation. So what we see, we get nothing traveling backward, but we generate a pulse, which contains all the frequencies that we're interested in. It's quick enough. But we generate a one-way pulse. It hits our device. Some of that reflects back. Some of it keeps transmitting. And you'll notice that backward reflected pulse will pass through our total field scattered field, or the place where we inject our source, just like nothing was there. And then when it hits the boundary, it disappears because of our perfect boundary. And that's it. So that is what the total field scatter field type of source looks like. It's a one-way source. So this is a pretty important slide, and this is where we describe the grid strategy and where we place all of these different things that we have to do on the grid. So we start off with a very simple one-dimensional grid. I'm only showing a dozen cells here or so. A real grid probably contains about 200 points, but it gets a little bit unreasonable to show here for what I want to do. So the first thing is we will seek out the entire grid and find the maximum and minimum refractive index. We use the maximum refractive index to calculate grid resolution because we want to know the minimum wavelength, and we'll use the minimum refractive index for the Courant stability condition to calculate our time step. But we seek the entire grid to find those. Next, we incorporate our perfectly absorbing boundary, and we need to know the refractive index right at the boundary in order to implement those. And we also need to know that when we calculate our time step that ensures our wave goes one grid cell in exactly 2 time steps. Then we choose where we want our total field scatter field interface. So we choose it way over to the left somewhere. That leaves a good bulk of the grid left to put our devices in. And so the cell immediately after that interface is in the total field region. That's really where we're injecting our source. And we need to look right around that total field scatter field interface for the permeability and permittivity, because we need those to calculate the electric and magnetic field amplitudes. Remember, the electric and magnetic fields have different amplitudes potentially depending what materials they're in. So we need to know those material properties. But there will be no source to the left of that dashed line. Then we hit a wave off a device, it leaves the grid, and we record that. At the very left side of the grid, we're recording reflected points, reflected fields. At the very far side, we're looking at the transmission points. We're recording transmittance at that last point in the grid. So reflection is recorded to the left of the total field scatter field interface, and the transmittance is recorded at the far right side of the grid. Well, then we'll build in some device into the middle of that. Maybe it's a whole bunch of different layers, or who knows what that is. But our wave will then start at the injection point. It'll hit that device. Some will transmit, and some will reflect. The reflected stuff gets recorded at our reflection point at the far left side of the grid, and the transmitted fields get recorded at the far right of the grid at that transmission record point. The last point I want to make is it's always good practice to include a bit of space between your device and your boundaries. Now, in our one-dimensional model here, because our boundary condition is working so good, these actually aren't needed. They're not numerically needed. However, for one-dimensional models, I like to include those anyway because I like to visualize the fields that are reflecting off of the device and transmitting through it. If we move the boundaries right up tight against the device, we would miss that. And also, when we move to 2D and 3D models, we will need those spacer regions. So it'll get us into the habit of doing that, but not technically needed now. And so how do we size those? We look at, one, how big do we want them to be? Maybe we want them big so we can visualize it. Otherwise, we'll look at our lowest frequency that we're interested in. We'll look at that longest wavelength associated with that lowest frequency, and we make those spacer regions about a wavelength. Later on, when we get to 2D and 3D grids and we need these, what we'll see is that the devices we're modeling, if they're resonating, they're generating these evanescent fields, these decaying fields that decay on either side of the device. And the boundary condition we're using, we don't want those evanescent fields to touch our boundaries, and so we need those spacer regions to make sure that doesn't happen. Now, in this case, our perfect boundaries, they're perfect, so we don't technically need those spacer regions. So here is our total field scatter field framework. On the left for a general 2D grid, and on the right I'm showing this for our 1D grid. And we still divide it into 2 points, two regions, the scatter field region, total field region. But remember, at each of these points we have 2 update equations that we're implementing, one for E and one for H. So if we're writing an update equation for this point, that point's in the scattered field. However, one of those update equations will contain a term from the total field. That's not compatible with the other terms, and we need to fix that. Likewise, when we're down here in the total field, one of those update equations will contain a term from the scattered field, which is not compatible with total field quantities, and we need to fix that. So we're actually incorporating our one-way source simply by fixing those update equations, and that's what injects our source. So let's talk about these corrections. So right now, we are on the scattered field side of the interface, so we're looking at the update equation for the H field at this point, right at the edge of our total field scattered field interface, but we're in the scattered field side. So we want all of the terms here to be scattered field terms. However, we have an electric field term from the total field side. That is not compatible, and we need to fix that. So we will take that term and we will subtract the source from it. Since this is a total field term which contains the source and scattered fields, and if we subtract the source from it, that difference is a scattered field quantity. So now our equation works after subtracting the source. The next thing we can do is take that source term and bring it to the outside of the brackets. Now something very interesting happens here. We get our original update equation back. That's really important. We've moved this correction off to the outside. What this tells us is that we can implement our update equation just how we've been talking about without thinking anything about total field scatter field. So we can sort of compartmentalize that bit of complexity, implement our update equations across the entire grid, and then when we're done that, we just simply subtract this little correction term from that one point in the grid, which is sitting right at the edge of the total field scattered field interface. Now we're sitting on the total field side, again right at the very edge of this total field scattered field interface, and now we're looking at the update equation for the electric field. Well, this is in the total field region. We want all terms in this equation to be total field quantities. Well, it turns out we have a magnetic field, we've reached to the other side of that interface, and now we have a scattered field quantity amongst a bunch of total field quantities. Well, we need to fix that. And how do we make a scattered field quantity look like a total field quantity? We add the source to it. So that's exactly what happens. We take our scattered field quantity and add the source. If there was a source there, what that would look like, we add it to it. Now we have a total field quantity. And just like before, we'll take this source term and bring it to the outside of the square brackets. And the same thing happens again. On the left, we have our original update equation. This means we can implement our update just like we've been doing before we even thought anything about sources across the entire grid, and then just subtract this little correction term from this one point in the grid. So from the last two slides, there's two source terms that we need. We need the magnetic field from the scattered field side, and we need the electric field from the total field side. So a lot of things are happening here. One's E, one's H, and if there's some kind of permittivity or permeability that's not free space, these will be of different magnitude. They're also existing at different times, and they're also in different position, and we need to compensate for all this when we calculate what those functions should be. So let's go back and think about the amplitudes. So let's start off with the electric field being the fundamental thing, and then calculate the amplitude and phase of everything else for the magnetic field. So let's say we start off with our source, the electric field, just being a sine wave, and we'll make it unit amplitude. That's very common in modeling. So it has a frequency term and a spatial term. This describes oscillations in time, and this describes oscillations in space. So this is our frequency in radians per second, omega. T is time, Z is position on the grid, and B is our propagation constant. So B very much takes the role of omega, but omega is a time frequency, beta is more of a space frequency. What we want is the equivalent thing for the magnetic field. What would be the E and H pair that would describe a wave traveling through our 1D grid? Well, potentially there's a different amplitude. We know it'll have the same frequency and the same propagation constant, but there could also be a phase difference between the two. So what we need to do is go back to Maxwell's equations and figure out the amplitude and phase, what's going on there. So we go back to our equations, our reduced set of equations for a one-dimensional case, and we see how they're related. We substitute in our sine wave for the electric field, and we get out exactly what should happen. So for the EY-HX mode, we see that the amplitude term for the magnetic field is negative the square root of the relative permittivity divided by the relative permeability. So in other words, if we're in free space where we're injecting our source, this whole square root term would just be 1, and we just see that the amplitude of the H field is inverted, 180 degrees out of phase with the electric field. And the phase is 0. In fact, for both cases, the phase between those two will be 0. For the EXHY mode, we get really the same conclusion, but there's no negative sign here. So remember, these two look the same, except there's a negative sign here. So, and the mu's and epsilons here are the mu's and epsilons at the position of that total field scatter field source. So now we've used Maxwell's equations, we related the amplitude, the phase term 0, we're ready to construct our source. So how do we calculate them? Well, let's start off and just calculate the electric field, being some Gaussian. So this is the same Gaussian that we talked about last time. Now all we have to do is calculate a magnetic field that has consistent timing and amplitude that is a solution to Maxwell's equations. So here's how we calculate the magnetic field. And this is for the EXHY mode, and on the other side is the EYHX mode. So for EXHY mode, the amplitude is this positive square root ratio. And also our Gaussian now has slightly different timing. And why does it have different timing? There's two components here. The E and H fields are a half time step apart. That's how we've defined our finite differences. They're also in physically different spots. They're a half cell apart. So we have these two delays that we have to compensate for. Same thing for the EYHX mode, except now we have a minus sign out for the amplitude. That came from Maxwell's equations. But we have these same two terms. We have the delay through a half grid cell, and we also have this half time step. Notice there's a positive here on the EYHX mode and a negative here on the EXHY mode. So we have these negative signs that we have to keep into account. But the reason we have this little messier expression for H is it has to be a solution to Maxwell's equations, and we have to get the timings right. Or we'll end up, if we get it wrong, what you'll see is we propagate energy backwards. So if you run your total field scatter field source and you see anything propagating backwards, somehow you have a sign or a mistake here that makes the E and H that you've chosen not a solution to Maxwell's equations. And so in order for FDTD to actually satisfy Maxwell's equations, there's some backward wave. So what do these actually look like? Well, if we calculate them, the pulse functions for E and H look really similar, particularly for the EXHY mode. In fact, if we plotted them, we really would barely see any difference. And if we zoom way in on the peak of this, what we can see is that there is this slight skew delta t. And in this case, for these particular input parameters, it's 3.5 picosecond different. So they look really similar, but they're slightly different timings. And for the EYHX mode, where we have that negative sign, we see that they're 180 degrees out of phase, but there's also a small delay. So if we zoom in on those pulses, we see here there's about a 10 picosecond difference between the two. So, and it's really important to get that right. If we get that timing wrong or the amplitude's wrong, we'll see some kind of power propagating backward from our source. So that's the telltale sign that we have something wrong with our total field scatter field source. Okay, so now we are masters of the total field scattered field source, and so now we have these pulses crossing our boundaries, and we want to calculate Fourier transforms. We're recording this impulse as a function of time. That's our impulse response. We want to Fourier transform those now. One thing we could do is just record those fields as a function of time. So if we were to model a very simple device, just a slab of dielectric, we hit it with a pulse, that pulse will bounce back and forth, and on the reflected side what we'll see is a series of ringing. And on the transmitted side we also see a series of ringing. We could record these as a function of time and then use an FFT to Fourier transform them. And here's our reflected field, and here's our transmitted field as a function of frequency, and here's also if we Fourier transform our source. Now there's a few things here that we need to talk about. One is that it's not usually practical to record these as a function of time. We may have 10,000 time steps. For a one-dimensional grid, only recording at 2 points, not such a big deal, but in 2 dimensions and 3 dimensions, suddenly there's a whole lot of points that we would have to record at a whole lot of time steps in order to do this. So what we'll do is calculate the Fourier transforms a different way, so we don't have to record over all of our time steps. We're calculating the Fourier transforms as we go. Another thing I want to point out here is that notice the reflection drops with frequency and the transmission drops with frequency. So we have to think, is this device reflecting less at the high frequencies or transmitting less at the high frequencies? How could it do both? How could it transmit and reflect less at higher frequencies? And the answer is, this is a false answer. If we look at the spectral content of our source, we see that the energy actually drops in the source. So what we're looking at here is not really a drop in reflection. We just see less reflection simply because there's less power in the source at these frequencies. Likewise, since there's less power in the source, we also see lower transmission. So somehow we have to normalize our reflected and transmitted Fourier transforms to the spectrum of the source to flatten these out. And that's what we'll talk about. Okay, so we have fields and pulses leaving our boundaries. We are recording them as a function of time. And we want to somehow calculate Fourier transforms as the simulation is running. So how do we do that? Well, let's start off with the equation for a Fourier transform. So this converts some generic time function in time, and this could be the electric field, magnetic field, or both, into that same function in the frequency domain. So if we are recording the field, let's say on the reflection side, what we get out is essentially reflection as a function of frequency. Or on the transmission side, it's transmission as a function of frequency. But we only know our fields at discrete times. So when that happens, this integral equation becomes a summation. And we use our function value at discrete times, and we're multiplying by this exponential that will become what we'll call our kernel times dt. So this is the numerical integration for this symbolic integration up here. Then what we want to do is rearrange things. We don't want to keep multiplying by dt, for example, because this does not change. So this can come to the outside of the summation. Likewise, exponentials are rather slow to calculate. So what we can do is factor out the delta t term, the m term, and what we're left with is this exponential raised to the m power. We can calculate this exponential ahead of time. So we'll call this our kernel, and this is specific to the frequency that we are Fourier transforming. So we'll get out that very specific frequency. If we're interested in a sweep of 100 different frequencies, we'll need 100 of these different terms, and we'll be doing 100 different integrations to calculate 100 different frequencies. So here's the anatomy of this. That multiplication delta t, as I mentioned, we can do this at the end. It's simple enough. If we included it in there and just multiplied by delta t each time step, probably not that big of a deal, but it's best practice just to do what's inside the summation in your main finite difference time domain loop, and when all that is done, just multiply everything by delta t. That exponential term we're calling the kernel, and every frequency that we're interested in obtaining from our Fourier transform has its own kernel. So we'll calculate that, we'll get some strange number, and we just keep using that. We'll raise it to the m power, and in this case m is the time step, so that'll go something like 1, 2, 3, 4, 5 as the program runs, the model runs. And wherever we're interested in Fourier transforming, we grab that function value that we're showing as f sub m, we take our kernel raised to the m power, multiply those two, and then just keep adding it to a total that we've initialized to 0 at the beginning. And that happens during the time loop, and when all that's done, we take that overall summation, multiply by delta t, and we have our Fourier transform. So here's how I visualize what is happening. At the top here, we have our grid. And we will be recording the reflected fields at the far left side and to the left of this total field scatter field interface. And we'll be recording the transmitted fields way on the far right-hand side of the grid. So this is our real space grid. And what we'll do, we can imagine if we want a Fourier transform and we want to calculate 12 different discrete frequencies. We will need to calculate 12 different kernels, and we will be storing an array of 12 different numbers associated with this block in the grid, and 12 more numbers, which will be the transmitted fields, for the transmitted side of the grid. And inside each one of these, we will be tallying and adding up a Fourier transform. We do that on the reflected and transmitted side. So that's how I visualize the data as we're calculating it. Let's put this into block diagram form. And we start off, we've eliminated a lot of, we're just not showing a lot of the basic FDTD steps. And so what we're doing here is concentrating on the steps really just associated with the Fourier transforms. So the first thing is to calculate all of the kernels. Remember, there is one kernel for every frequency of interest. If we are Fourier transforming, let's say, 70 different points in the grid, but all at the same frequency, that is only one kernel. We don't have to calculate a kernel for every point in the grid. It's just one kernel for every frequency we're interested in. Then also for every frequency we're interested in and every point, we need to initialize a Fourier transform to 0. Then we enter the main FDTD loop, and you can imagine update H from E from H, so the basic finite difference time domain engine. But within the loop, after all the updating is done and sources and all that, then we update the Fourier transforms at all of the points and frequencies that we're interested in. And then, of course, this iterates over time. And when this is done, we still have yet to multiply these Fourier transforms by the delta t. That's the last step. And once we do that, then our Fourier transforms are complete. And we can plot those and see transmission and reflection as a function of frequency. So here's some MATLAB code to go with that. We will start off and define an upper frequency. So we'll call that F2. So we want a Fourier transform up to 5 gigahertz. So we are going to simulate something and calculate its reflection and transmission from 0 up to 5 gigahertz. And we'll plot that. So the first thing then is to initialize all the Fourier transforms. Well, freq here is an array containing all of our frequencies. So then what we do is we calculate k, and if we include this freq array, k comes out being an array of all of the kernels that we need. There's one for every frequency of interest. The next thing we'll do is initialize all of our Fourier transforms. So we have an array for our reflection side, we have an array for our transmission side, and here we're also calculating the Fourier transform of the source. So we actually have 3 arrays. Then we have our main finite difference time domain loop. So we're looping over the number of steps. And of course, there's a whole bunch of code under here that's performing the FDTD functions, updating the fields, doing the boundary conditions, incorporating the sources, all that sort of stuff. Once all the updates are done at a particular iteration, then we're ready to update the Fourier transforms. And we're just adding. So reflectance equals reflectance plus our kernel raised to the t power. Remember, t is an integer that will go 1, 2, 3, 4, 5 as the simulation's running. And we multiply it by the field where we want the Fourier transform. So in this case, it's EY at the first point. So we're Fourier transforming the reflected field. And we loop over frequency. So that's exactly what's happening. We're updating the reflection array. We do the same thing for transmission, but here we're looking at the electric field at the end of the grid, at big NZ. And then, of course, to Fourier transform the source, we're not looking anywhere on the grid. We're just grabbing whatever the source is for that time step and Fourier transforming it. Well, then we may want to visualize, but that's basically the finite difference time domain loop, focusing in on the code just for the Fourier transforms. And of course, we chose here not to multiply by dt here. We could have, but a little bit better maybe to do it after the loop is over. So it's just one step. So once we multiply by the dt, then we are finished, not before. Your results would give crazy numbers otherwise. Okay, more about calculating reflectance and transmittance. All we've done so far is just Fourier transform the fields at the reflected and transmitted side. It's not yet reflectance and transmittance. So that's our next subject. So reflectance is the fraction of power reflected from a device. So it should be independent of how much power is in the source. We're just calculating what fraction of that power from the source is reflected. Likewise, transmittance is the fraction of power transmitted through a device. And so if we are ignoring losses or gain, completely passive materials without loss, if we add reflectance and transmittance together, we should get 100%. That's a conservation of energy requirement. So the little plot here is just showing what we might see from a particular device, what transmittance and reflectance looks like. And we can see by this, if we add them up, that we will get 100% all the way across. So let's go back to the response of the device. Pretend for a second we had actually recorded the field at this first point as a function of time, and it would look like this. And if we used an FFT to calculate the Fourier transform, here's what the reflected spectrum would look like. And notice it rolls and drops. If we looked at the transmitted side, we would see our series of pulses. This series of pulses is here because our source pulse is bouncing around and slowly transmitting or reflecting. So we see those pulses, the ringing within the device. And if we FFT this data, we also get this spectrum that sort of rolls off. Now it would be easy to say, oh, well, this device must be transmitting less at higher frequencies and also reflecting less at higher frequencies. But that's not true. If we look at just our pure source and look at its Fourier transform, we see that the power in that drops with increasing frequency. So really, it's not the reflection that's becoming less and transmission that's becoming less. That's only because there's less power in the source at these higher frequencies. So we want to remove this artifact, and we do that essentially by dividing by the source spectrum. So how do we do this? Well, the first thing is we calculate our basic Fourier transforms. Remember, in our MATLAB code just a few slides ago, we had 3 Fourier transforms happening. We had our transmitted field on the far right side of the grid, our reflected at the far left side of the grid, and we are also Fourier transforming our source. So the way this is all compensated, we will take our Fourier transform for the reflected fields and divide by the source Fourier transform. And this removes the fact that there's less power at certain frequencies within the source, and we get something that looks much more flat. And we do the exact same thing for the transmitted fields. Let's see what that looks like. So when we do this for the reflection side, we see we get a much flatter looking spectrum. If we do it for the transmitted side, we also see we get a much flatter looking spectrum. And all we've done is divide by the source. Now if we add these two, assuming we have not put loss or gain in our model, we should get 100%. So that's exactly what we're plotting here is conservation. And you'll notice this black line right at 1 or 100%. And that's a really, really good indication that our model's working. If conservation was off, that's one of two things. It's either a mistake in our code or we have power stuck in the model somewhere. There's something resonating and we need to run longer until that leaves as either transmitted or reflected. But this is something we should always do in our models. If we're calculating reflectance and transmittance, is add them together and make sure that all of the energy is accounted for. Even if I'm modeling something with loss or with gain, I'll build my device. I will turn that loss or gain off initially, run the simulation, make sure that I get conservation. Because if I don't, then I know something's wrong somewhere. And then I can turn it on, and if I have loss built in, I would expect that conservation curve to dip down to less than 100%. If I have gain built in, I would expect it to come up above 100%. So we can still use some common sense to try to ascertain whether things are working or not. So once we Fourier transform, let's think about the frequency axis. From the Nyquist sampling theorem, we know based on our time step, delta t, that there is a certain maximum frequency that we're going to be able to resolve, and it's 0.5 over delta t. So just due to the Nyquist sampling theorem, we will not be able to resolve frequencies higher than f max. So if we set up our time axis this way, we're going 0 to steps minus 1 and steps of dt, this will give us an array telling us what time each of those time steps happen. Then we record our field, we Fourier transform them, and when we Fourier transform them, we not only use an FFT, we use an FFT shift. That places the DC component in the middle of the array instead of at the edge. So it looks a little bit more pleasing. But now that we have this Fourier transform, we want to plot it versus frequency. How do we do that? Well, we'll calculate this maximum frequency. It's 0.5 over dt. Then we create our frequency axis. How many points are in this axis? Well, when we FFT a function, the number of points does not change, and the number of points is steps. So we're using this linspace command with steps. Since f max is the maximum frequency we can resolve, and we're going from negative to positive frequencies in our Fourier transform, this must need to go from negative f max to positive f max in some number of steps. So this is how we'll calculate our frequency axis. In this formulation here, steps should be an odd number. If it's even, you'll be off by a little bit. It's still possible to create a correct frequency axis. We just need to compensate for that. But it's easy enough just to make steps odd, and then this works. Now, another thing that's easily confused, we have two main source parameters. We have the time step, and then we have the number of steps. The upper frequency limit is set solely by the time step. If we just run for more iterations, we're still not going to be able to resolve any higher frequency than f max on this slide. So it's the time step that determines the highest possible frequency that we can resolve. And in reality, we wouldn't want to try to resolve this frequency right on the hairy edge. We would probably want a delta t that's even smaller than this, so that we're more comfortably resolving it with maybe at least 10 points per that shortest wavelength. And if we follow the rules of thumb that I've outlined, your delta t will be very sufficient to resolve the highest frequency that you're interested in. Okay, so the time step determines the maximum frequency that we can resolve. Now the resolution, how finely we can resolve frequency, is set by the number of steps and also the time step, but I tend to think more in number of steps. The time step will be whatever it is, but the resolution, number of steps. So we will run for more iterations to resolve more frequency steps. Think of it this way. Your frequency axis goes from minus f max up to positive f max, but the number of points is steps. Remember that on the previous slide. So clearly, if we have more steps, more time iterations, we will be resolving frequency more finely. So what's the cost of that? Well, if we need to run more iterations, that means our simulations will take longer. So resolving frequency very finely can be difficult. Another thing I'll mention on this slide, it is possible up front to calculate kernels for very, very finely spaced frequencies. And at first glance, it might seem like we're resolving that. However, we're actually not. By truncating the number of time iterations, it's like we're convolving our frequency response, the actual real frequency response, with a sinc function. We are blurring that, and that's really what's limiting our resolution. We can go in and calculate frequencies spaced as tightly as we want to be using the recipe we outlined a few slides ago. However, the information will be blurred, and there's only so much resolution we can get out of that. Even though we calculate them very finely spaced, they'll be blurred and not really contain the information we think. So even though we can do that, we need a large number of steps to resolve frequency very finely. So that's an important point to remember. Okay, so let's look at a movie of what we'll see on our Fourier transforms. Here we're calculating these transforms as the model's running. So we see our pulse, it goes into the device, reflects a little bit. On the plot above, the blue line is the electric field, the red line is the magnetic field. On the plot at the bottom, the red line is reflectance, the blue line is transmittance, and the dashed black line is the sum of the two. So let's see what happens. Suddenly here our conservation is way off. That dashed black line is going below 1 and above 1. That's because there's power still stuck in the device, and we need to keep running to wait for that to leave the device, cross the boundaries, to be incorporated into our Fourier transforms to be counted as either transmission or reflection. So the longer it runs, the more that conservation line flattens out. And this is another reason why we always look at that conservation line. If that's not perfectly flat, there's either something wrong, we haven't run the code long enough, or maybe there's loss or gain in the model. So remember this movie. This is what we expect to see. And that conservation can deviate significantly from 1 for a variety of reasons, mostly that there's power still stuck in the device. Okay, let's pull all this together and revise our finite difference time domain algorithm. Our initialization now, we calculate grid resolution, we'll calculate our time step, we'll calculate our update coefficients, and we'll initialize all the fields. We've broken that down into more detail in previous block diagrams. Then we calculate the source. We have some upper frequency that we want to resolve, and we're calling that f sub c. So we can calculate the duration of the source so that it contains sufficient power at that highest frequency. Based on that duration of the pulse, we calculate the delay, and that's 5 or 6 taus. That ensures that we'll ease into the source and ease out of it. Then we'll calculate a Gaussian with that delay and that duration and just make that the electric field of the source. Then we calculate the amplitude and the time delay of the magnetic field, and then calculate an equivalent magnetic field. And we plotted these two together, and we saw, other than a potential sign difference between the two, that they look exactly the same. There's just a very, very, very small time difference by this delta t. And these equations here are for the EY-HX mode. Then we initialize our Fourier transforms. We set all the Fourier transforms to 0. We calculate all our kernels. Remember, we have one kernel for every frequency we're interested in. For the Fourier transforms, we have one Fourier transform going for every frequency and one for every point. Then we initialize our boundary terms. We have these perfect absorbing boundaries, so we'll initialize all those terms to 0. Then we enter our loop. And as normal, we update h from e. Remember, this is our big time domain loop. For t equals 1 to steps, or 0 to steps minus 1. We update e from h. Remember, this is another for loop that's iterating over our grid. So we update e from h. Then we've done the updates. Now we incorporate the correction term for our total field scatter field source. Then we record the h fields at the boundaries. Now that's essentially updating all of h. Then we update e from h. We incorporate the correction for the total field scatter field. We record the electric fields at the boundaries. At this point, we've updated the fields. That's done. So now we could update our Fourier transforms. Here I'm explicitly showing the dt, but we could not include that here and incorporate it after the loop is done, after the time loop. But I'm showing it here. Then maybe we visualize the fields, and this just keeps iterating. Update h from e, handle the source, update e from h, handle the source, Fourier transforms, visualize the fields, and we just iterate until we're done. So that's our revised FDTD algorithm with the perfectly absorbing boundary, with the total field scatter field source, and with Fourier transforms. So I want to leave you with some tips on visualizing an FDTD. I always like to show the materials and the fields at the same time. Now, for simplicity, you don't have to superimpose them. In the movies, you saw that I did superimpose them. I really like doing it that way. It also gives you a higher level of intuition of what's happening because I feel like I can actually watch the fields bouncing off the different interfaces. So that's my preferred way. And you can go back to our MATLAB lectures to figure out how we're doing that. We're essentially plotting the device. We use the hold on command, plot the fields, and then hold off, and things are superimposed. You probably also want to show all of the field components that's happening. because if things are going unstable, it may be happening with one of your field components before the other, and it can help you isolate where the problem is. They'll definitely both explode, because if one begins to explode, so will the other. But very often, if you slow your model down, you can see it happening to one of the field components before the other, and that'll help you isolate what's happening. Also remember, if we're updating graphics at every iteration, that can really slow down your simulations. The graphics is really, really slow. So a few things you can do is only update maybe every 10 iterations. Or you can use some of the timing commands in MATLAB and only update every 30 seconds or something like that. Maybe you choose not to do any updates once you know everything's working. I also always display transmittance, reflectance, and the energy conservation. Particularly the energy conservation. That is really, really important. That's one of your best tools to know if something's going wrong. Now, just because we get conservation of energy doesn't necessarily mean things are right, but if we don't get our conservation of energy, that definitely means things are wrong. So it's always, always good practice to include that.